All right, does anybody have any questions about anything? Yes. Yep. Um, well, let's look at the sim. Wait, so the question was on page 172. When you, oh, is that right? Oh, it should be. Damn, another typo? Let's find out if I missed that one. That was page 172. Nope, I don't have it. Crap, that's another one, huh? So make sure I get this right. This should be 25, and you base that upon 1 over the simulation time, which was 500 nanoseconds, so that's 200 kilohertz. And 200 kilohertz out to 1 over 500 nanoseconds. Yeah, 2 megahertz. Yeah, so 2 megahertz in 50, so that'd be 25. So why did Eon, what did you get for the number of points here? You didn't get 32? Are you able to plot the data out in a table and look at it? If you look at the output, like view output, there may be a table where it says frequency and then value. Did you look at how many points were there? Well, let me just look real quick. I think what you're saying is reasonable and right. Um, yeah. Did you do that? And it was 25? All right. Well, I'll just change it in the book. So what does that do to the example, though? That says that instead of square root of 32, so what's 32 square root? So it's off by 0.65. So this would be, yeah, it'd be slightly less. Oh, come on. What is it going on today? Well, it's my computer. I brought it with me. So this will be a little bit lower. Yeah, about a millivolt. No, just eyeball it. I just said approximately. Yeah. I mean, if you want to be more exact, what you do is, and I did this since you'll see in the later chapters, is there's a MATLAB script and it reads out the values at each of the points. Yeah, and then sums it up to get an exact value. But I mean, you have to, when you're teaching and you're going through stuff, if you are too overwhelmed, you have to do things gradually and then lead into them, or else they become, I'm dying here. So this is just an eye. And all of their point here is I wanted to make sure nobody was looking at this going, how do I calculate the noise? I mean, you should be able to look at it and go, okay, the noise is approximately this, right? Just by eyeballing and get an idea. And you can go back and say, okay, what if it was 75? How does it change? Or what if it was 76 or whatever, Yeah, or 73 or whatever. All right, so let's go. There are no other questions on the homework. It was all straightforward. All right. Okay, so let's talk about improving. Today's October 6th, 2014, and let's talk about improving. Is the coherent sampling thing, is that all making sense? Like you were Does everybody understand why you do coherent sampling? Well, let me ask a question. Going back to this figure, would you say there's coherent sampling used to generate the noise in this plot? No. How do you know? Yeah, it's random. It's not got individual tones, right, where you do the windowing and they don't bleed into one another. So this isn't coherent sampling. Whereas if you look at a spectrum like this one, you can really see the individual tones. It is coherent sampling. All right. Any questions on the jitter or the signal to noise plus distortion ratio? I got a question. We'll see if anybody remembers. What is the other name for, if you look in, like, I think Analog Devices uses this term. If you look at SNRD, signal to noise plus distortion ratio, what's another name for that? Yeah. What does that stand for? Yeah, signal to noise and distortion. These are equal. Okay. How do I go from SNDR to just SNR? Sometimes you say signal to QR, SNQR. What is SNQR? These are all trivial things. I just want to make sure we've said it so that if you see them, you're not, oh, well, I've never seen that term before. This is signal to quantization noise ratio. So it's the same thing as SNR, except you're removing the tone. So you don't do SNRD is where you leave the distortion tones in, and SNR is where you remove them, so all you have is the quantization noise. So sometimes you see this SNQR, okay, but it's the same thing as SNR. And so you got to be careful here with specsmanship, because when people give, results of data converters and things like that, they could give SNR, which could be great, but then the SNDR or the spurious-free dynamic range could be crappy, so don't let them feed you a line. You got to make sure it's, this is considerably less useful than this one. Because you're removing information to make the spectrum better when you go to this one. Okay? Yeah, so you look here and you say, okay, if I have SNDR, that's what the output spectrum looks like. I remove the tone of my input signal, but then if I have nonlinearities, that gives rise to harmonics in the spectrum. Okay? If I go, well, I want the SNR alone, then the SNR is not only removing the fundamental, but also removing the harmonics due to nonlinearities. So all you have left is the noise. And so you might ask, well, why do I care? Why would somebody ever do that? Why would they care about SNR? Okay? Well, one reason is what happens is your input signal starts to drop. The input amplitude of the input signal starts to drop. Well, so do the distortion tones, right? And so then the distortion tones go down into the grass. They go down into the quantization noise, and they don't become an issue. So then the SNDR and SNR are the same. Does everybody follow that? And I think I put a plot in here where you can see that this kind of says what I just said. As you go to lower signal amplitudes, SNR and SNDR are the same because the distortion terms become small. And so you still care about it, but then as you get to bigger amplitudes where the distortion terms start to grow up, they're the weeds, they're the thistle that sticks above the grass. They're the ones that you care about. They're no longer below the top of the grass. Okay, any questions on that? Okay, and last quick review. Any questions on the jitter discussion? If I look at this, which I don't think I covered too well, if I look at this probability density function here, this was the case where the jitter was equally likely to fall within minus del TS over 2 to plus del TS. What is del TS equal to? Yeah, it's your maximum peak-to-peak jitter, del TS, right? And this approach is just like what we had with the quantization noise approach, but in the quantization noise approach, that was fine. It was this was a valid probability density function, because why should the noise be, if you're putting in a random signal, why should it be here versus here versus here? But for the jitter, It's not a good probability density function because the jitter is going to have a shape which is not flat. It's going to likely have a peak-to-peak value and then some Gaussian shape, and we covered that later right here. And the problem with, and I'm not going to cover this in any more detail, but the problem with the jitter is, and if you go through here, if you're like, okay, I'm going to design a cell phone and I'm going to use a clock that has a certain phase noise requirement, and you look at the distribution of where, or has a certain phase noise, and you look at how the edge jitters on the clock and say it's even sinusoidal, what happens is that jitter is then modulated up to the carrier, and so it actually influences how tight you can place the channels when you're transmitting information. And just as a repeat myself here just to make sure everybody followed, what was the example I gave of this earlier when we were talking about IQ signals? Remember when here, let's pull it up. Remember when we went to Wikipedia and we pulled up the constellation diagram, right? So we go to IQ modulation, and you look and you say, okay, here by changing the amplitude of the in-phase and quadrature components. Okay, so let me ask some simple questions here just to make sure, because this is really topics for a communication class, but since we're designing circuits that are used in communications, we need to know this. If I ask you, how am I changing the phase of the signals there, like if this is a 16 QAM, 4 different bits, how do I change the phase of the signal? Yeah, it's simply changing the amplitude of the in-phase and the quadrature component. How do I change the phase between the I and Q signals? I don't. One's in phase and the other's quadrature out of phase with it, right? I'm just changing the amplitudes. And if I change the amplitudes, what happens? Of course, you could argue, well, how do you get to here, for example, or how do you get over to here? You're changing the amplitudes. And you could argue, well, if you go negative in an amplitude, doesn't that change the phase? Okay, but if I ask, does anybody not understand this diagram? If I change the I and the Q, I can select one of these points. If I increase the amplitude, I can move out. If I shorten the amplitude, I go here. Okay, and I'm changing both of them. If I make the quadrature stronger, it moves up here. Make the same amplitude of the in phase, but I reduce the quadrature, it moves down here. Okay, I got a question. So going back to the reason I brought this up, what is the point of, or what is the jitter do to this constellation diagram? I mean, this is a very big deal in like Qualcomm or anybody making cell phones. Why is the phase noise and jitter of the clock such a big deal? Okay, so if I go back here and I read this discussion, what happens is when you get a distribution and this is a reasonable approximation Gaussian shape, what happens when you take that and you're using it on a data converter and you put in a single tone, say a carrier, that jitter modulates to the centered around the tone that you put in. Okay, and you can go through the discussion here. Well, if it does that, and I'm trying to digitize an IQ signal, which is what everybody wants to do. They want to move the A to D converter right to the antenna so you get your signal coming in on the patch antenna in your cell phone. You digitize it because once it's digital, you don't have all those analog problems. But you got a clock that doesn't have perfect phase noise. You start to modulate or get that noise right around the signal, and it increases the size of this dot. So if I have phase noise, the dot starts to expand, and you say, well, what's the big deal? Well, I want a big margin between these adjacent points here. I don't want them to start to leak over because then I start making bit errors. Does everybody follow that? So instead of it being a nice, well-defined dot, my jitter starts making the voltages move around because I'm modulating the amplitude. That's exactly what I'm seeing right here. I'm modulating the amplitude of the signal, and then that's causing errors. So if I go look, I think they had a plot here. Let's see if they do. Let's go back to Uh, Here, I'll show you what. I got a student that did a PhD in this stuff. Let me pull his dissertation up. Boom, where he did digital tunable surface acoustic waves. Let's go quickly down and look at the constellation diagram. And I'll show you, he did a really good job with ch5 simulating it right here. And you can see here's a constellation diagram with no phase noise, and then here's one with phase noise, and you can see how the size of the dots start to increase. You start to get more jitter. And if you look at, well, why is it worse out here? Well, these are bigger amplitudes. Okay, so you can see what's going on. So just out of curiosity, how many levels of QAM is that? Yeah, 64. Okay, all right. So let's move on. Each one of these topics is super important practically, but I mean, realistically, we have a finite amount of time. So try to read those and go through it. I don't recall, I think I might have assigned some homework on that, but what we want to do is move on to this topic next, which is improving SNR using averaging. Okay. All right, so I want to, just before we even get going on this, I just want to qualitatively discuss something and make sure that you follow. So if I take an ADC and I clock it at F sub S, and I've got an input. Then I take another ADC and I clock it at 2F sub S, and I've got an output here and an output here, and they're both the same size ADC. And I ask you, what is the difference in the quantization noise? Is the RMS value of the quantization noise different in these two cases? So this is something, the reason I'm presenting this right now is because this was a conceptual thing I had a problem with when I was learning this, so I want to make sure it's really clear. Is there a difference in the quantization noise RMS values? No. The RMS value is VLSB over root 12. Has everybody got that? But if I look at the spectrums, what's the difference? Yeah, this one, the noise goes to F sub S, and this one, the noise goes to 2F sub S. No. The RMS values are the same, but the power spectral densities are different. I'm sorry, this would be F sub S over 2 and F sub S, 2F sub S over 2. Okay, so if I add up the area here, that gives me an RMS value of VLSB over root 12. Same thing as if I had this area. So I'm spreading the noise out over a smaller, or I'm spreading the noise out over a wider band. I'm not increasing signal to noise ratio. Does everybody get that? Just by clocking faster, it spreads the quantization noise out over a further distance, but it doesn't reduce the signal to noise ratio. Okay, so now I'm going to go back and I'm going to put two ADCs in parallel, and I'm going to clock each ADC at F sub S but on opposite phases of the clock so that I get an effective clocking of 2F sub S. Then I'm going to talk about the quantization noise in that case. And the thing is, when we do that, we're going to get less quantization noise. And we need to understand why, and at this point you should know how to describe it. But does everybody understand this point? Okay, so let's go do that. So here I take an ADC, and I've got my input, and it's clocked at F sub S. And I go down here to an inverter, so I get F sub S bar. I'll be sloppy, the notation. And I go over here, and I've got an ADC. And I go up, and I take my, let's go back to a DAC. And then I look at that. All right, so wait a sec, I got a question. Before I even look at the spectrum here, whoops, let's average this. So we'll call this V out 1 and this V out 2 and this V out 1 plus V out 2 all over 2. I got a question. Wait a sec. This doesn't make sense. This one has a spectrum which looks like this. This one has a spectrum which looks like the same thing. But I know if I put these two together that I'm going to get less quantities. I'm going to get a ADC that samples at 2f sub s, but hey, isn't the spectrum going to be changed then? But wait, how can I be stretched out here to 2f sub s over 2, or Nyquist frequency? What's going on there? Does everybody understand the problem? Okay, so I want to, before we go on, I want to ask, okay, would everybody agree we showed this basically behaves like an ADC clocked at 2f sub s? Okay, so I've done something a little tricky here. I've added these resistors, but if I want to get this spectrum, what I need to do is I need to alternately select this ADC, then this one, then this one, then this one, then this one, and back and forth. And I'm not doing that. What I'm doing is passing the outputs through an averaging filter. So I'm passing this through an averaging filter, which is what, effectively? It's V out 1 plus V out 2 over 2. But in the Z domain, how do I write that? How do I write this equivalent operation if I were to do it in the Z domain before I go back to analog? This should be trivial at this point. How do I write the Z domain equation for an averager? No. Boom, I'm done. This is out over in, so I'm averaging the current sample and the next one and outputting it. Except you could argue, okay, well, to be more precise, I put the 2 in there. Does everybody follow that? So if am I losing anybody? Okay, so if I ask, what does the frequency response of this look like? Then it looks like a comb filter. It's a full delay. I'm not being precise. I'm assuming that this is clocked at 2f sub s. So coming out, it's 2f sub s, meaning that one clock cycle would be half sub s, t sub s on this clock. Does that make sense? So here I'm going like this, and then on the words coming out are changing at a clock rate of t sub s over 2. Okay, so if I plot that though, what do I get? And we're going to cover this more in a moment, but what I get is the following. Here is my original quantization noise, and then now I'm running it through this filter, which now if I normalize it to 2, looks like the following. So I've gotten rid of all this extra quantization noise. Does everybody follow that? So I expect that my RMS value of quantization noise is going to go down, but what's the cost? I'm throwing out any high frequency signals too. If I put signals out here, they're being filtered just like the noise. But you say, okay, well, if I can increase f sub s, that still could be useful. Okay, so let me go over this again. But before I do, are there any questions? So the whole point is, we know that averaging, like 1 minus z to the minus k over 1 minus z to the minus 1, that sink filters, is a low-pass filter. If I take a quantization noise spectrum and I run it through a low-pass filter, I expect to filter out the quantization noise and to improve my signal-to-noise ratio. Does that make sense? Yay? Nay? Why don't we do an example before I move on? Let's do 514. Because I don't see anybody going, oh yeah, I get it, it's perfect, it makes total sense. Okay, so we'll go do 514. And what? 520, did I download the wrong one? 520, oh no, that's right. 527. Okay, so here, and you know what? Let's do this a couple ways, all right? let's play around with this. Let's just run the simulation, but before I do, here's my clock signal. Let's go over here, right click on it, highlight net. Does everybody see here I'm clocking this ADC path and this one's clocked out of phase? So effectively I'm getting out a spectrum here which is has 2f sub s. Now before, and we can show this, but before I go on, if I go look at the spectrums here on the output of the ADC, like I plot the output spectrum V out A or the output spectrum V out B, do I expect to see spectrums like what I drew here? Do I expect to see, oh, they go out to, where is it? They go out to f sub s over 2 and then they go down nice and flat, right? No, I don't expect that, because that's my way of faking things and saying all the noise is in the spectrum of interest. But if I look at the spectrum here, I'm going to see that the output has a wide spectrum of noise. Is everybody cool with that? I've covered that well, right? So no one's going to say, but the here, let's do it, because I'll hit run, and then let's just plot this guy right here. There's V out A. We go view FFT, and we go OK. And then let's go out to, how about 200 megahertz? And I look and I say, hey, wait, my Nyquist frequency is 50 megahertz, which is right here, but the noise doesn't disappear like I've been drawing. Well, of course it doesn't. It's my tool that I'm using and assuming that the noise all fits in down here. Does it roll off? Sure. Okay. All right, so if I go back now and I look at the output here, what do I expect the spectrum is going to look like differently from what I just showed? What I just showed was nice and flat. What do I expect here? Well, okay, no one's screaming the answer. What do I expect when I run it through an averaging filter? Yeah, I expect it to roll off at f sub s over 2, right? Because as I get closer and closer, why? Explain to me intuitively, why do I expect the noise in the signal and the output that I'm about to plot to roll off at f sub s over 2? When one input's going high at f sub s over 2, the other's going low. When I add them together, they subtract out. Right? My digitizer gets it here, gets this here, and I put it through that averaging filter, and it says, hey, plus 1, minus 1, I get 0 out. Of course, it'll be 1 and 0, so I get the common mode voltage out. Does everybody follow that? So I'm going to go look now at the spectrum. Am I losing everybody? Okay. Does it make sense, Wenlan? Is it making sense? You're worried about your test tomorrow? Why do professors have tests? All right. No, what you're probably thinking is, damn, you give a lot of grading. I can't keep up. All right. So we'll look at that, and then we'll go look, and hey, what's going on here? Let's go plot it where we can see a little better. 200 meg. And what is it doing here at 200 meg? Let me make it a little further out so we can see it rolling off towards 0. Why is it out here at this frequency instead of down here? And why is it the tones are coming out, or why is this one out here? What's up with that? Well, it's the sampling frequency is 200 megahertz, right? So let's see. Let me go over here, and I really want it to be pronounced, so why don't I go linear? And I can't even see it when it's linear. Let me see, log decibel. Well, you can see it rolling off, right? Okay, so I got a question. Why isn't it precisely at 200 megahertz? Why is it slightly off? If I go investigate, what do I think I'm going to find? Well, let's go investigate and see. Well, I'll tell you what I think is going to be the issue is that the rising edges of the clock aren't perfectly spaced at 5 nanosecond. They have finite times, and so it's not perfectly 50% duty cycle. But let's find out. Let's go look at clock here and clock bar, and then zoom in because we won't be able to see anything. And I look and I say, okay, let's go here. Let's go left 0, right 20 nano. Okay. And let's see. So here I go up at 5.6 and here 10.1. Oh, it should be 10.6. Crap. I got to adjust my clocks because they're not perfectly 50% duty cycle. Does everybody see that? So that's why it's not at 200 megahertz. It's slightly off. No magic. Any questions? Well, I got a question. If I want to show this or show that I get less noise, what could I do? What's another way I could show that averaging gives me less noise? I could use an averaging filter, right? Okay, so let's do that and then we'll quit on doing this. So let's go and let's go here. Let's get rid of this. Let's get rid of this. Let's get rid of this. And let's get rid of this. Go in here. Then we'll come up. Go over here. Make sure I did that right. Highlight nets. Looking good. So far, they're both the same. Okay, now what I'm going to do is I'm going to go stretch this guy out. So here's my control experiment. Here's my one that I'm adding stuff to. Now what am I going to do? Don't all scream it at once. I want to get rid of quantization noise. What do I do? I want to put a filter in there to filter some of the quantization noise to show that I get less RMS quantization noise. So I'm going to go to my library. I'm going to see what I have available because I don't want to go. So how about 8-bit comb filter? Looking good? And since you guys have been using this, does the input, does it automatically, do I need to put 2's complement here? Or does it do it inside? Let me just look. It does do it inside? Really? Where? BDI, B7, B... Oh, right here? No? So I'm asking, I don't remember, I haven't used this cell in a long time. Do we need to do it 2's complement out here? How is this 2's complement? What? Yeah, we have to, that's what I'm asking. Do we need to complement the MSB to change it to 2's complement? Because it's not done inside here, right? Okay. All right. I'm asking something easy. So we'll go to inverter. And inverter, is it this one? Or is there a small one? This one? All right. That one looks good. And you know what I'm going to do? Because I don't want any timing issues. I'm going to put this here. Then I'm going to get I'm going to go over here so that... oh, wait. I don't want to do that, do I? I do not want to do that because I want to clock these together. Do I need it? Is there a race condition here if I do this? I used to know these backwards and forwards, and since I haven't used them in a while, I don't remember. Is there a race condition? So I clock the ADC. You know what I'm thinking here? I'm saying there isn't a race. So if I clock the ADC, this value comes in and then it goes to the output. Well, we'll find out if we see glitches. Okay, tell me what else to do here. No, that's what I'm asking. because there's no delay in the comb filter, the signal goes right through, so I'm going to clock them together. So the output of this will change, and then I clock that in here. Okay? So tell me what else. What's that? Alright, but does it work with just an 8-bit DAC? If I just move the DAC up here and copy this, is that going to be okay? If I just go, oh, let's... Yeah, but can I use... Okay, let me ask a simpler question. Can I use this 8-bit DAC here? Of course not. I'm trying to show I have less noise. I need to have a wider word, right? If I have I'm not trying to show my signal grows. I don't get 2 out of here. I'm trying to show I have less noise. The only way I have less noise is if I have more bits. Okay, so I got to use a different DAC. So let me get out the scissors. And then I go here, and then let me get the 12-bit or 10-bit DAC. That one, look, works good. Let's move this up. I'm just making sure everybody can use these components so there aren't any issues. And I move this down. And then what do I connect the LSB to? Yep. Alright. We ready? Nope. Oh, yeah, thank you. Okay. And, okay, so wait. What do I expect to see? This path here and here is exactly the same. But what is this dude going to do? Yeah, so let's sketch it. So what we should see. So we should see the top one having a spectrum that looks like this for the noise with an input signal sticking up in the... But my bottom one has a comb filter, and so it's going to have zeros at 12.5 megahertz. So I'm going to get a spectrum that does something like this. And roll off because of the digital filtering, right? So if I add up the noise in that spectrum, I should get less noise. But let's find out. You know what let's do? Let's do File, Save As. I'll post this just in case you want to play with it. Example. So we go Run. And we go, let's see here. Boom. Let's see here. Okay, so what I was worried about, the reason I plotted those is because if the signal was too high and I ran it through that comb filter, what happens? Yeah, the digital filter, the comb filter is going to reduce the output of that second signal. And I also wanted to verify that I didn't make any mistakes with the wiring. Alright, it's like watching paint dry. It's good times. Okay, so we'll go out here and then we'll go select the top, then go to View, FFT, V out A and V out B, OK. Let's just go out to 100 megahertz. What the heck? What happened here? That ain't right. Yeah, but oh, you mean here? Oh, yeah. I didn't see that. Yeah, let's do that just to see. So does everybody see the issue? Because of the delay. So just out of curiosity, how many clock cycles should I wait? How do I know? Yeah, I need to wait at least 8 for this guy to catch up, right? Because I'm getting garbage out. 8 clock cycles, 80 nano, so I'm going to wait 10 nano. I'll go back to here, and I'll say start saving data at 100 nano. And I hit OK. We'll hit save just to be safe. So we don't want this to be in our spectrum because it's an error. So we hit run. We'll watch the paint dry again. Okay, I want to actually do example 515 in just a sec, which is I want to integrate the noise spectrum here. Because, we can show going through here that this is the result, but I want to actually derive it a separate way. So if I use okay, so this is a good example. If I use a filter that averages 4 points, so k is 4, so 1 minus e to the minus 4 over 1 minus e to the minus 1, I expect my RMS quantization noise to drop by a factor of 2. Okay, so talk to me about that. What are the assumptions? So say I work in industry and I'm going to design an oscilloscope, and I say, you know what, I'm going to take a 6-bit ADC in this scope, and I'm going to run the output of the ADC through filtering, and I'm going to increase the signal to noise ratio. Tell me why that doesn't work. Well, even more fundamentally, what happens when I put a DC signal in? Does any of this stuff work? No. Because if I put a DC signal in, I'm getting the same quantization noise out. My filters passes everything at DC, so I haven't got any benefit in signal to noise ratio. Does everybody follow that? Meaning I got to satisfy Bennett's criteria. If I put in a little signal that's lower than the LSB of the data converter, does that work even though it's busy? No. So keep in mind that what we're covering right now has limitations. So we're going to fix those limitations in the future, but it's still useful. Okay? And then, as Rob said, we also get the signal. If it's at a high frequency, then it also reduces the signal. So it doesn't give us effectively more signal to noise ratio because we drop the signal along with the noise if it's a higher frequency signal. So is everybody clear on the limitations? This only works if I got Bennett's criteria met and my signal's busy. Okay, so let's go back and see what we get this time. Oh yeah, let's do add plot plane, pull this up, and wait a sec. Yeah, it's hard to see the difference in the two, isn't it? You can definitely see here that, it's quite a bit lower, but to really guess or to really see what the difference is, you really need to do it numerically and look at the values by themselves. This isn't as... What's that? Can't you plot? What do you... You mean in a time? Yeah, but the problem is it's going to be millivolts because the LSB of the data converter is only a millivolt, so seeing it with your eyeball is going to be really tough. Well, the problem is... What? Oh, whoops, I don't want this one. You mean here? Let's try it. I don't think it'll work because it's... Yeah. Oh, wait. V out. That's not right. I guess you'll just have to see. Yeah. All right, we'll do it. Well, the problem is the reason that all of these things I'm hesitate. Well, you tell me, what's the reason I hesitate to do any of them? Well, here, I'll give you a hint. What is it? Yeah, well, no, not the long run. But when I put the filter in there, what's another thing that I do to my signal? We always talk about magnitude, but there's also phase shift. And so I phase shift the second signal. I got more delay of that signal. So if I try to take the difference, it's not going to work. Does everybody follow that? So I'd have to try to fiddle around with the delays to get it out here. Okay, that's why later you have to go to MATLAB and you take the output of the LT Spice and you read it into MATLAB and then you massage it that way so you know exactly what the data is at each point. Okay. All right, so let me just repeat this one more time and then we'll do that derivation. And so the whole point of this is that we take the spectrum that we have in the quantization noise that looks like the following. We assume it goes to the Nyquist frequency. We run it through the filter, which takes and does the following. Whatever. And so this is F sub S over K when we do our averaging, so it removes all of this quantization noise. So, what's that? Or K, yeah. So, if you ask, all right, well, what's the benefit if I have the following? I can then go through a digital filter and my SNR will go up because I removed the noise. But that only works if my desired signals are down here and busy. But the concept is there, and we're going to use it when we talk about noise shaping modulators for doing A to D conversion. Okay, are there any questions? Okay, so let's do this and prove that our quantization noise becomes 1 over the square root of K times VLSB over the square root of 12. And that was the standard deviation of the noise when we looked at the probability density function. And just remind me, what did the PDF look like for this, for the quantization noise? Yeah, it's just a flat quantization noise spectrum. And what are the limits? Yeah, VLSB over 2 minus VLSB over 2. Righto? Okay, so let me, from last time, if I do a averaging and I ask what happens to the spectrum. Okay, we'll ask a simpler question before I ask that. Here's my PDF. Oh, what was the amplitude here? Okay, if I ask what's the standard deviation of this? Okay, this is where I know these are trivial questions, but I just don't want anybody getting through the class and not being able to answer them, so that's why I asked. So what is sigma? Yeah, VLSB over root 12. And what is sigma squared called? Yeah, the variance. Okay, I know that's boring, but I just have nightmares. Well, what's the standard deviation if I'm looking at quantization noise? Okay, so now, if I do the averaging, if I'm averaging points, what does it do to the spectrum? Or so what does it do to the probability density function? Yeah, it makes it higher and narrower, so it does like this. So then what happens? My standard deviation gets reduced by the root of K. My variance gets reduced by K. So if I on the test a week from Wednesday, if I put those simple short answers, you'll be like, he's not challenging me. This is easy. Any questions? Okay, so I want to go through and do this mathematically and prove that indeed this is the correct equation. Okay, so before I do, what is the value of my quantization noise here? Let's do it in power. One-sided spectrum. What is the quantization noise power spectral density? VLSB squared over 12 No, there's no k. I'm just asking without averaging. Okay, what does this have to average to if I integrate it, the power in this spectrum? No, it's a spectrum. This is F. What is this? If I sum this up, if I integrate from 0 to F sub S over 2, what does it add sum to? What is it? Yeah, it's Fs. If I put the 2 here, or if I'm using a one-sided spectrum, I could use 1. Here, let me show you that plot in here. Right here. So VLSB over 12 times 1 over F sub S. Does everybody recall that? Where we're going to F sub S over 2. And then this would be 1/2 of that. No, nothing challenging there, right? Okay. So, and this would be, if I had the 2 there, that would be 4. Yeah, one-sided spectrum, okay? All right, so let's go and look at example 515. So example 515, and we're going to take just an averager, 1 plus z to the minus 1, which has a transfer function of 2 times cosine of pi f over fs. We know our quantization noise can be written as of f is equal to VLSB squared over 12 times 1 over f sub s. And so what we're going to do is we're going to integrate. We only need to worry about this between 0 and f sub s over 2. So we're going to integrate 0 f sub s over 2. And then we'll use one-sided spectrum, obviously. VLSB squared times 2 over 12 divided by f sub s. And then times, and then I'll rewrite this as why did I do it that way? See equation 129. Why did I switch cosines there? Oh, duh. I left off. When I integrate the spectrum, I have to square the filter transfer function. Okay, so I'm integrating the power in the spectrum, so I've got the following. So I've got my power, which is power here, P is power spectral density, and then my filter transfer function I have to square. So this becomes a squared term. So using that trigonometric identity of cosine squared, I can rewrite this as 2. Did I lose anybody on that? Okay, so I got a question. Why is this? Why am I here? So this would be squared, magnitude squared. So why did I use 1 plus cosine of 2 pi f over f sub s here? Where did this come from? Yeah, it's the cosine squared because I'm running it through power, so the filter transfer function's magnitude squared. So when I square the filter transfer function, take the magnitude, I get cosine squared here. So then I use the trigonometric identity from equation 1.29 and I get this. And then of course, what did I leave off here? Over frequency. And so if I integrate these terms, so let's feel the pain and do this nice and slow. So VLSB 4, 3, so this becomes VLSB squared over 3 times f sub s. Is f sub s an integration variable? No, 1 over f sub s evaluated at 0 and f sub s over 2. Whoops, I left off the f here. The integration variable. So the f sub s fall out, and this goes to what? VLSB squared over 6, check in the book, and then I do the same thing here, VLSB times the cosine, so I get VLSB over 3 times 1 over Fs, and then what's this in the denominator? How do I pull that out? What is it? F sub s over 2 pi times sine of 2 pi f over f sub s evaluated at 0 and f sub s over 2. So what does this become? 0. And so the overall term is then equal to VLSB squared over 6, or 1 over 1/2 times VLSB. Whoops. What is that? Uh, yeah, I got it. Um, yeah, but I did that here, so this would be VLSB. Oh, wait. Yeah, so this is squared. And then it doesn't matter because this goes to 0. But did I do this wrong in the book? I think this is right, isn't it? I mean, here, look in the book. So this term, sine is 0, 0, sine of pi is 0, so this term goes away. And then it's just VLSB over 6, right? I'm not seeing any issues. Is there any issues? All right, and then it says here, wait a sec, that's not equal to what we derived. What we derived is 1 over k, but the thing we didn't put into the equation here when we did it is that the filter transfer function went up by 2, and then when it goes up by 2, the magnitude of this goes up by 2, and this goes to 2, and so if we do that, then the SNR comes out correctly. So I know I lost everybody on that, so let me pause for a moment. Go back up here and ask, well, wait, before I do that, let me make sure. Does everybody understand this result here? So VLSB squared over 6 is not equal to 1 over k VLSB squared over 12. And so we expect that this would be actually, for averaging 2, VLSB squared over 24. So it's off by a factor of 4 in the denominator. So where did the factor of 4 come from? And the answer is, well, here with the filter we have a gain of 2, but we didn't put that gain of 2 in the signal. So if we put the gain of 2 in the signal and we square that, we get a factor of 4. So then we're back on track. So our 2 VP here is not VP, it's multiplied. So let me put it in really simple terms. When we put the signal through this 1 plus z to the minus 1, we multiply it by 2. So instead of our peak being VP over 2, centered around the common mode, it becomes essentially 2VP over 2 because we're multiplying the signal by 2. So that's what I did here. It's 2VP divided to make it RMS, and then it goes to the right value. Did I lose anybody here? Did I keep anybody on the train? Make sense? Angshuman? No? No? Okay, so let me ask you this. Do you follow up to here? Alright, so this is right, but this isn't equal to the equation that we had right here. We said this is the amount of quantization noise we have. It's VLSB over 6. So the RMS value here, let's not fight it. The RMS value is VLSB over root 6. I just took the square root. Then here I said, well, wait, you forgot, buddy, that when you pass the signal through that filter, 1 plus z to the minus 1, the magnitude goes up by a factor of 2 because you average the signals, right? So then I take VP, and instead of using VP, I multiply it by 2. So it's 2 VP. So then with some simple algebra, it ends up giving me the quantization noise that I thought I should get in the first place, which is VLSB over root 24, which is effectively after I normalize the signal. Any questions? Whole point of this was, oh, okay, well, if I go through this derivation, then I should end up with VLSB squared over 12 times 1 over k for the variance, for the mean squared value, and I don't. And the thing is, well, we forgot that we're also multiplying the signal. I think it's clear, but if it's not, I'll try to explain it again. I think it's really clear. Damn, it's clear. Okay, let's cover one more topic and then call it a night. Does anybody have any question on this? So you should be sitting going, okay, well, averaging can increase the signal-to-noise ratio if I remove part of the spectrum. And all I'm simply saying is if I pass the output of a data converter through a digital filter, it's a low-pass digital filter, I can remove part of the quantization noise. It makes perfect sense. Okay, but the input signal has to be busy, and it has to be bigger than 1 LSB, or else I don't benefit from averaging. Okay, so there's limitations on this approach. So you might ask, well, why are we covering it? And we'll use it in the next coming chapters. You'll see where we can fake or make our input signal appear busy with feedback. Okay. All right. So last topic, or actually 2 quick topics. I just wanted to really cover how averaging works. Your ADC has to actually be accurate to the final resolution that you want to average to. So if you have ideal outputs here and here, it's fine, you average right in the middle, but you can imagine if your ADC output starts to drop, then so will your average point, and it'll give you errors. So the bottom line here and the takeaway is that if you want to try to take a 6-bit ADC, and you meet all the requirements with the input signal being busy and large enough and all that, and you want to get 10 bits resolution by digital filtering, your 6-bit ADC has to be 10-bit accurate. Okay, that's an issue. So that's why when we start using the delta signals, we're going to use 1-bit ADCs and DACs, because then they're perfectly linear. Because 1 bit, you get 2 points, you don't have any non-linearity. So we can get 20 bits, no problem, because we're perfectly linear. Okay, so does everybody understand this issue? I can't average to try to get to 10 bits. Imagine I'm getting 10 bits. If this was a 6-bit, that means I'm getting 16 levels in the middle. Well, I can't do that unless these 2 points are within 10-bit accuracy. Okay, so again, another issue with this approach. Any questions there? So I got a question. If this was 1 millivolt and this was 2 millivolts, and this was 1 LSB, and my ADC had 1 millivolt LSB, and I wanted to get 4 extra bits, what would that mean as levels in between this 1 millivolt and 2 millivolt? I need 1 millivolt, 1.0625 millivolts, 1.125 millivolts, 1.1875 millivolts, 1.25 millivolts, and so forth. In other words, these points have to be very accurate. So the takeaway there is, once again, the averaging has to be as linear as your original ADC. Any questions? And again, why the hell is he teaching us? This is not really benefiting. If I can make a 6-bit ADC that's 10-bit accurate, then why can't I just make a 10-bit ADC to begin with? All right. Okay, last topic is this one. This is common in some signals, especially in audio, where what you do is you add a noise dither. And you try to add this noise dither, which means you're adding a signal to your input. And you do that at a spectrum here that's outside your desired spectrum of interest, so that when you listen to your song or you look at your signal, it doesn't corrupt it, because then you can remove this with the filter. So I want to graphically just show you. If I take a DC input signal and I put it in and I do averaging, it really doesn't benefit me because I've got the same output every time. I get this code or this code, I average it to. I can't see what the average is, if it's closer to this level or closer to this level. Well, if I put in a noise dither, which is truly random, and it's going to sometimes, if this level moves up, I'm going to actually be up here more often than I am down here. So when I do the averaging, I'll get an average which is closer to this output code than to this output code. So this is a common way for you to increase your resolution without using a higher resolution ADC. Does everybody get the idea? Okay, you're simply moving. If you put the dither in, it's going to come up here a little bit more than here if the signal's slightly up more. And then what that's going to do is when you average it, the average will be closer to this level than to this one. Okay, and so here's a way to add the noise dither. So it's a noise you're adding to your input signal. You're summing the dither with your input signal, and then you're digitizing. And then, so here's an example of a random dithering signal. And then you take the output of the signal here and you run it through a digital filter to remove the noise dither. Does everybody follow that? And so you remove the noise dither, but what you're left with is a signal that's a better representation for your input. All right. Any questions? Are we covering enough information? All right. This chapter here we're going to cover feedback and all that next time. But this chapter here is where we're going to start really getting into some useful stuff. I mean, not that what we haven't covered hasn't been useful, but we'll get to utilize for the rest of the semester. We'll start getting to utilize the techniques that all these DSP and things that we're covering. So if you can, try to read this, and then we'll move on from there. When we come back next time, the first thing we're going to do is we're going to spend some time talking about using feedback to improve SNR. So you can put in a DC signal here, but then with feedback, you can make it appear that it's busy. Have a good day. We'll see you on Wednesday.